Hello, welcome to Unit 6, Lesson 3, Ready, Set, Go, More Sign Language. So the first problem on the Ready section says, the circle has been divided into equal portions. Explain the meaning of each number in the equation. 30 degrees divided by 306 degrees equals 1 out of 12. So if we look, I guess I'll start right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 segments. So it's saying that this theta is 1 out of the 12. So that's what the 1 over 12 is saying. Well, if we know a whole circle is 360 degrees, then if we divide that 360 divided by 12, we get 30. So that means that this angle must be 30 degrees since it's 1/12 of the circle. So that is the meaning of question 1. All right, it gives us a little note right here. In Math 2, we learned how to find the arc length of the portion of a circle when we are given the measure of the intercepted arc in degrees and the radius of the circle. We can find the fraction of the circle using n degrees over 360 degrees, where n degrees is the measure of the intercepted arc. Then multiply the fraction of the circle times the circumference. So, use the information in each drawing to find the arc length of the intercepted arc on the circle. So let's look at the first circle. It tells us that we have a radius of 7, and it outlines that the amount of the circle we want, this green area, that's 1/4 of the circle, or 1/4, right? 1/4 of the circle. 1/4 of 360 degrees is 90 out of 360, but we could actually use 1/4 because this proportion, this 90 over 360, is always the amount, the percentage of our circle times circumference. Circumference. Right, so if we know our radius, so 90 over 360 is the same thing as 1/4 times 2 pi times our radius, 7, right? So we can reduce 1/4 and 2 to get 1/2 pi times 7, or 3.5 pi feet is our arc length. Arc length. Now let's see if it mentions. So it doesn't mention rounding. So we'll just round however we feel fit. So this is the exactly. So this is our exact value. And if we actually do 3.5 times pi, we get about 10.9955. So I'll round that up to 6 feet approximate. So approximate arc length. So there we have it for question number 2. So question number 3, it tells us that the length of this green arc is 135 degrees. So it's 135 out of the whole circle, 360 times 2 pi times 12. And we know we're in centimeters because it tells us that the radius is 12 centimeters. So 135 divided by 360, that comes out to 3 over 8. Right? So it's 3/8 of the circle times 24 pi. And 24 and 8 divide really, really nicely, right? 24 divided by 8 is 3. So this leaves us with 9 pi centimeters exactly. Or if we want to actually do the decimal approximation, we can go ahead and multiply that value by pi. Which gives us about 28.27. We did 3 decimal places the last one, so I'll do 3 again. 274 centimeters approximately. Okay, question 4. This gives us the angle measure of 270 degrees. So 270 degrees divided by 360 times 2 pi, and our radius is 9 meters. Now, 270 divided by 360, that's about 3/4 of our circle, right? 3 out of 4 of our quadrants there. So times 18 pi meters. So 3/4 times 18 gives us 13.5 pi meters exactly. And to get a decimal approximation, we multiply that by pi, which is about 42.4115. So I'm going to round it up to 2 meters approximately. Right, and it didn't tell us how many decimals to go to, so if your answers were actually slightly different than mine just because of how much you rounded, that's acceptable as well. And question 5. So it tells us that we're using 343 degrees out of this whole circle, out of this 360. So times 2 pi, and it tells us our radius is 8 inches. So 343. 343 divided by 360. Those do not have a common factor, right? I'm trying to think. There's no common factors there, actually. So we can just go ahead and simplify the 360 with the 2 or the 8, right? So 360 divided by 2, if I want to simplify there instead, right, I can make that 180. And then if I want to simplify with the 8, I can divide both by 4. So I can make this 2 and this 45. So let me kind of regather our thoughts here. 343 degrees out of 45 degrees times, and we're left with just 2 inches here. 2 pi inches. Sorry, I forgot my pi. Pi inches. So since those don't calculate nicely, we'll just, or don't divide nicely, I should say. So our exact answer would be 686. Yeah, that's double 343 pi over 45 inches. So let's do our approximate here, right? So if we take that number, we do that 686. Or we could always start over, right? And do 343 divided by 360 times 16 pi. But if we do that number, we get about 15, a little bit over 15 times pi, which gives us about 47.89, and then it's 1/8, so I'm going to round it up to 2 inches. Okay, let's move on to our set problems. So set says a right triangle has been drawn from a point on a circle centered at 0, 0, and the angle of rotation, theta, has been drawn between the initial ray and the terminal ray. So it says write the value of sine of theta as defined in today's lesson. You'll need to find the radius. Use right angle trig to solve for angle W inside the triangle, and use the measure of angle W to find the measure of angle theta, the angle of rotation. Okay, so we have that this point here is 4, 3, right? So that's actually our x and our y. It's also our adjacent side, right? This is the same distance as x, so our adjacent side is 4. And our opposite side is 3. That's how high we went. So if I want to find our hypotenuse here, since our sine ratios, right, is opposite over hypotenuse, I want to make sure I calculate that. So let's do Pythagorean theorem. 3 squared plus 4 squared equals our hypotenuse squared. In this case, I'll call it a radius since we're dealing with a circle. So we get 9 plus 16 equals our radius squared, so we get 25 equals our radius squared. The square root of 25 is 5, so our radius here, radius is 5. And I don't see any units here. So sine opposite is 3 over our radius or hypotenuse, 5. So x over r. Right? Not x, sorry. Y over r. It's another way to think of it. So angle W. So notice theta and W are actually the same. The question asks us to find both. But to find that W, we want to do inverse sine of 3/5. That's going to give us our W because it's going to give us the angle that it takes to create this 3/5 ratio. And that's actually going to be the same for both of these. In this case, they're exactly the same angle we see here. So inverse sine of 3/5. If we go to our calculator and do that, make sure we're in degree mode. If we want, actually, I guess we could give our answer in a different mode, but I'm going to give my answer in degrees. So for answers in degrees. So if I put my calculator in degree mode, I get about, let's see, does it ask us to round anything? No. So 36 point, I'll go to a few decimal places, 8, 6, and then it goes, the next two numbers are 8, 6, 9, 8, 9. So let's go to 2 decimal places. We'll go to 8, 7. Okay, and that's going to be true for both. So 36.87, and I want to make sure I include my degree symbol for those values. So there is question 6. Let's go down to question 7. So question 7, we have an x value of -4 and a y value of 4√3. So sine, again, we need to find our hypotenuse. We might actually recognize that these ratios are the ratios of a familiar triangle, but let's just calculate them. -4 squared plus, right, because that's this distance right here, plus 4√3 squared is going to give us our radius squared. So we get 16 plus 16 times 3, r squared. Well, 16 times 3 is 48. Or really, we can think of this as 16 times 4 if we add all those 16s together. But 16 plus 48 equals r squared, plus another 16 is going to give us 64. 64 equals r squared. Well, the square root of 64 is 8. So you might have actually recognized that as a 30, 60, 90 triangle right away, which if you did, wonderful. If you didn't, that's okay. We're going to get that now. So sine is our y value over our radius or our opposite, 4√3 over our radius 8. So now the W, this is where these are different. So in problem 6, these weren't different, but this is sort of the reference angle here. Because this is going to give us the angle in the triangle. When I do sine inverse of 4√3 over 8, that's going to give me the small angle within that triangle. So if we take out our calculator and we do 4 times the square root of 3, divided by 8, we do get that 60 degree angle. So this angle right here, this W is 60. Now we know that we start at 0 here, and that this angle right there is 180. So we're 60 less than 180, right? So 180 minus 60. So this angle right here is going to be 120. So the theta angle is 120. Okay, question 8. So we have x is square root 2 over 2 negative, and y is negative square root 2 over 2. So again, we might actually recognize that when those two sides are the same, we have an isosceles triangle, and since it's an isosceles right triangle, we're going to have a 45, 90 triangle here. But even if you can still do Pythagorean theorem to find the radius. Let me organize this a little neater. Negative square root 2 over 2 squared plus negative square root 2 over 2 squared equals r squared. Well, square root 2 squared is just 2, and 2 squared is 4. So we get 2/4 plus 2/4 equals r squared. Well, 2/4 plus 2/4 is 4/4, or just 1. And the square root of 1 is 1. And our radius is a distance, so it's always going to be positive, right? X and Y, those can be negative because it's the location on this coordinate system, but our radius is always a distance, so it's positive. So sine, well, if we got a radius of 1, that means sine is just negative square root 2 over 2 divided by 1, or we can just leave it as negative square root 2. So W, again, that's going to give us this little reference angle. Let me highlight it, actually. I should have done that on the last one, too. Right, that W is that reference angle. So to find that reference angle, we can actually use sine inverse of negative square root 2 over 2. And let's see what that gives us. So when we do sine, of negative square root 2, we get negative 45 degrees. So let's kind of separate this off to the side. It gives us, when we do this, it gives us negative 45 degrees, right? And really what that means is that we're 45 degrees sort of below this axis here. It doesn't realize that we're not at 0. So it's giving us something that's actually this angle right here, negative 45 degrees. So we can know that in this triangle, we can use this positive 45 degrees as our answer there. And now to get theta, we think, okay, if this is 180, it's 180 below, sorry, it's 45 below 180. So we have to actually add that 45 onto our 180 degrees. So we get 225 degrees. Okay. Now, if I had used just square root 2 over 2, I would have gotten this positive 45 anyway. So if we had used the actual triangle ratios, we would have gotten the positive 45. Okay. Question 9. So 9 has an x value of 6 square root 3 and a y value of negative 6. So again, we're seeing some special right triangle ratios there. But if we want to solve for r squared, we can do that. Excuse me. There we go. So we have 6 root 3 squared plus negative 6 squared is going to give us our radius squared. So this gives us 36 times 3 plus 36 equals r squared. So 36 essentially 4 times here. Right, 36 times 3 is 108. 108 plus 36. So that gives us 144, right? Yeah, 144. And the square root of 144 is 12. So our radius is 12. Again, we could have recognized that those are ratios for 30, 60, 90. So we could actually do W. We could do W without any calculations, but let's do our sine angle first. So our y value is negative 6 since we're below the x-axis. So negative 6 over 12. And let's reduce that to negative 1/2. So here, if we do sine inverse of negative 1/2, that's going to give us the angle measure, kind of, right? That gives us negative 30 degrees. But really, we want just the angle in the triangle. So for triangles, we're going to ignore the sign there, right? So that is negative 30 degrees because it's below 0 degrees, right? 0 degrees is here. So we're going to use 30 degrees since we're talking about the triangle. But we actually could use that angle for theta. Theta is negative 30 degrees, is coterminal to theta, meaning it's going to land us at the same spot. But since it shows us theta is this bigger angle, instead, let's think 360 degrees. Well, we're 30 degrees shy of 360 degrees, which means we're 330 degrees for theta. Okay, question 10. So question 10 says, describe the angles of rotation that make the y values of the points positive and the angles of rotation that make the y values negative. So let's draw a little grid here. Here's our positive y's, and here's our negative y, right? The positive y-axis, and let's color coordinate a little bit, and our negative y-axis. So that's negative y. So basically, for positive y values, the angle is between 0 degrees and 180 degrees, right? 0 degrees is here, 180 degrees is here. And that's in degrees, or we can say 0 and pi radians. So for negative angles, for negative y values, the angle is between 180 degrees, sorry. Between 180 degrees and 360 degrees, or pi and 2 pi radians. So I should do a little note on this. So note, at 0 degrees, at 180 degrees, and 360 degrees, y is 0. And I'm going to actually put, or 0, pi, and 2 pi radians. Y is 0. So it's neither positive nor negative. Now, when I say that, like, obviously we can have an angle that is much higher than 360. We would go to to a coterminal angle to try to determine that. Let me get this all on our page here. Just move it over slightly. There we go. Okay, question 11. What do you notice about the y values and the values of sine in the previous graphs? Well, here the relationship is if y is positive, so is the sine value. Is the sine value. If y is negative, so is the sine value. And we could even take this a step further and say, and now this wasn't from the previous graph, so I'll put in parentheses. If y is 0, well, sine will also be 0. Be 0. Because on those graphs, so the y value was the same length as the opposite side. Side of the triangle. that's why those were coming out the same, since our radius is always positive, right? And the radius is always positive, or the hypotenuse is always positive. Okay. Question 12. In the graph shown, the radius of the circle is 1 unit. The intersections of the circle and the axes are labeled. Based on your observations in number 11, what do you think the value of sine might be for the following thetas? And it gives us 90, 180, 270, and 360. So we actually kind of got at this a little bit, but here's our 90 degrees up here. So we have x over y. Since y is 1, sine, I'll say y equals 1. There we go. Since y equals 1, sine of 90 will also equal 1. Okay, let's go to 180. So here's 180 degrees. We have our xy. Since y, oops, that's not how you spell since y equals 0, sine of 180 degrees will also equal 0. Okay, so 270 is down here. So we have x and y. So here, since y equals -1, sine of 270 degrees will also be -1. And lastly, here is our 360, or 0, same as 0, x and y. So since y is 0, sine of 360 degrees will also be 0. Okay, let's move on to question 13. Make a sketch of the following problems, then solve. It says, a kite is aloft at the end of a 1,500-foot string. The string makes an angle of 43 degrees with the ground. So part A wants us to sketch this, and part B says how far above the ground is the kite? Round your answer to the nearest whole number. Okay, so let's do our best to sketch this. I'll use a graphing tool to help me a little bit. So let's do it. Yeah, sure, why not? So here is just sort of a little outline. Let's say this is the spool of the kite. So kite spool. Where the string comes out. So our string is right here. And it tells us that string is 1,500 feet. That's a lot of string. And then I'm going to draw a kite as best I can. So there's our kite. Now it tells us that the string makes an angle of 43 degrees with the ground. So we're assuming that this is the ground. Now we wouldn't really fly a kite from the ground, but maybe this is some type of special kite. It is extremely long string. So 43 degrees right there, angle between the string and the kite. So there's our sketch. So now it says, how far above the ground is the kite? So that's our question in part B. How far above the ground is the kite? Well, it's looking for this height. Now, because we're measuring the height above the ground, we can go ahead and assume that we have a 90-degree angle here. So we have the hypotenuse, right? We know that this is the hypotenuse, and we're looking for the side opposite 43. So let's go ahead and use sine. Sine of 43 degrees equals opposite, which is our x value. Or actually, let's do y. Yeah, I'll keep it x. I was going to say we could do y since we're looking for height, over 1,500. So the height is going to be the value we get from taking 1,500 and multiplying it by sine of 43 degrees, and it tells us to round to a whole number. So let's go ahead and plop this into our calculator. So sine of 43 degrees, that gives us something about 0.68 times 1,500 is going to give us 1,000 and 22.9975 or so. It says round to a whole number, so about 1,023 feet high. Okay, question 14. So a ladder leans against a building. The top of the ladder reaches a point on the building that is 12 feet above the ground. The foot of the ladder is 4 feet from the building. So let's draw this. So we're going to sketch it. So let's go this way, I guess. So here's our ground. Right? And it says the foot of the ladder is 4 feet from the building. So let's make that 4 feet, and this will be our building here. So let's draw in our trusty ladder. So here is our ladder. It's leaning. Okay, so the top of the ladder reaches the point of the building that's 12 feet above the ground. So we know this height from the top of the ladder. It's a building right here to the ground. We know that that's 12. We also can go ahead and assume that this building is structurally sound and it forms this 90-degree angle. So there is our sketch. It says find to the nearest degree the measure of the angle that the ladder creates with the level ground. So the angle that the ladder creates with the ground, we're talking about this angle right here. We know its opposite side and we know the adjacent side. So we're going to go ahead and use tan of this angle is opposite 12 over adjacent 4, or tan inverse of 3. So the angle is, now does it tell us to round, find to the nearest degree? So we're going to make sure we round to the nearest degree. But let's do our tan inverse first. So inverse tan of 3, that gives us about 71.565, since it says to the nearest degree, is about 72 degrees. Okay, question 15. So the shadow of a flagpole is 40.6 meters long when the angle of elevation to the sun is 34.6. So let's draw this sketch. Okay, let's do green again. I guess we have some ground in here. So let's put the sun. We'll do the sun in a orange color. Why not? So here's our sun. It's sun. Okay, so the shadow of a flagpole. So this is our flagpole here. Let's see, flagpole. Flagpole. So we're assuming the flagpole is structurally sound. So we're going to go and create a right angle there. And then the sun is creating this kind of invisible path here. So it's creating this invisible path, and says the angle of elevation to the sun. So it means we're elevating, we're looking upward. So from some flat surface, we're going to go upward, elevation. So that's this angle down here, 34.6 degrees. And it says that the shadow that the flagpole is creating is 40.6 meters long. So that shadow is going to fall on the ground. So there we go. There's a sketch of this diagram. It says find the height of the flagpole. So that's opposite our 34.6 degrees. And since we know our adjacent, right, this is adjacent and opposite, let's use tan. So tan of 34.6 degrees equals opposite, which is our flagpole, over 40.6. So the flagpole is going to be 40.6 meters times tan of 34.6 34.6 degrees. Make sure you are in degree mode too. We should, if you're using the same calculator that you've been using, you're probably all set already, probably already in degree. So tan of 34.6 degrees gives us something just under 0.7, right? 0.689, so on, times 40.6. That's going to give us about 28.008. So we've been rounding to the nearest whole number. So the flagpole is about 28 meters tall. There we go. There's question 15. So question 16 says the angle of depression from the top of the building to a car parked in the parking lot is 32.5 degrees. The building is 252 feet high. So let's draw this. Okay, so there's our building, and here's some parking lot. Okay, so here's our building. And we know that height is 252 meters. And again, we're going to assume that this building is structurally sound. Now, I'm actually going to draw more of a rectangle here because it says angle of depression. So that depression means we're looking down. So angle of depression from a flat surface is downward. So we have to be careful because that doesn't always fall inside of the triangle. But let's draw our parked car. So here's our sort of car. Not my best car drawing, but there's our car. Okay, so the angle of depression from the top of the building to a parked car is 32.5. That's this angle right here, because it's from the top of the building, 32.5 degrees. Now, because, and I'll kind of I'll close this off here. Since these are a 90-degree angle, I could actually say that this one is 90 minus 32.5 degrees. I could find that angle there by doing 90 minus 32.5. Well, 90 minus 32.5 gives us 57.5. So I'll put that in, 57.5 degrees. Since a whole triangle is 180, this angle down here is also 32.5 degrees. So that angle of depression from the top of the building is the same as the angle of elevation from the car to the top of the building. So the phrasing is really important. We have to make sure we're careful about that. So there's our sketch. I don't need to actually keep this dotted line in, so I'll take that away. Now it says, how far from the top of the building is the car on the ground? So it wants the distance from the top of the building to the car. So it's looking for this distance right here. So that's the distance top of the building to the car on the ground. So we're looking for the hypotenuse. So we could use sine or cosine here. It doesn't make a difference. And you can use either angle. So let's use, let's say I want to use this bottom angle here, then I need to use sine. I need to use sine of 32.5 degrees is opposite 252 over the hypotenuse, d. Or if I wanted to use cosine, I could say cosine of 57.5 degrees equals adjacent, which is 252, over d. So either works. So it doesn't matter which one you pick. For this one, we'd end up with d equals 252 divided by sine of 32.5 degrees. And for this one, it would be d equals 252 divided by cosine of 57.5 degrees. Right? So it doesn't matter which one you choose. So let's go ahead and plug those into our calculator. So both of these come out to approximately, I guess I'll write them each, 469.012, right? So 469.012, doesn't matter which way you do it. So the distance, how far the car is about, we'll round to a whole number, 469 meters away from the top of the building. From the top of the building. Okay. And that is our last problem on this Unit 6, Lesson 3, Ready, Set, Go. Thank you for watching, and hopefully you found it helpful.